All right, wait for it. Wait for it. It's coming. There we go. It is 2 hours UTC, which means once again it is time for Astronomy Daily Live. This is a daily live stream where a group of friends, an ever growing group of friends who share a common passion, want to turn the TV off, get away from the news, and look out to the universe and think about everything else. Um, share a common passion and sit around and chit chat about astronomy for an hour or so. Now, almost every single day, I have poised and ready. I have a tweet that goes out on Twitter. You can follow me there at Astro and Music, and I'm going to tweet this. I do this almost every single day. I have it all ready to go because when I go live, I want to go tweet like that because it's saying that I'm live, right? I want to tweet that I'm live. I'm going to do the same thing on Facebook. Boing, just like that. Those are two things that I very, very rarely remember to actually do because I have to do it, more or less as soon as I go live. And the problem with that is, of course, is that as soon as I go live, I am focused. I'm focused here, right? Not focused anywhere else. So it just completely, right? And I say goodbye at the end, and I stop the broadcast, and I go over to my Linux machine, and like, oh man. So tonight I did it. I did it. I tweeted and I Facebooked. Facebooked as well. Now, I don't know why, but yeah, all right. Anyway, just did that, so we're good to go there. I am going to open my live stream on my smartphone so I can monitor that. I pop out the chat? Oh, I didn't pop out the chat. See, there's always something. There's something new with live streaming, which I think I actually I when I started looking into live streaming, I there was looking at the help, right? Looking at the Google Hangouts help. Um, uh, I saw that there was this way to be able to do it on a smartphone. It's called webcam. It was I forget youtube.com/webcam, right? And on my smartphone, I typed in that link and it said it didn't exist. So I went over to my Linux machine and did exactly the same thing, and it said it doesn't exist. Well, now I just noticed, I think I noticed it last night for the first time. There's a new option under, um, let's see, if you go to Creator Studio, and you go to live streaming, there's an option that is called, dun, 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 what's it called? Camera. Camera. And apparently that's a webcam type of thing. So I'm going to be playing with that, investigating it a little bit more, and then seeing what that's all about here in the next few days. Um, I I think I already found a way to live stream uh, via my smartphone, and I don't remember why I opted not to do that. Oh, it was because I couldn't share my screen. I didn't have a screen to share, so I sort of dropped that for the moment. But I guess I'm going to get back into it um, and see if there's a way, some way to share the screen, because that's, for this live stream, show and tell, having uh, visuals is really, really important. Now, you may have noticed a subtle and slight difference in my background back here. You may notice that uh, everything, like everything on the wall, is a little lower. That's because the angle of the camera, of course, is tilted up a little bit. And the reason why it's tilted up a little bit is because I have finally, I think permanently, changed chairs. The chair that I have had for probably about 10 years, that I got at a at a at a sale at the um, University of Arizona. Um, they had this, this desk chair there, and it was like, I I want to say it was like $5 or $10 or something, and it was in okay condition. It was fine. Um, Picked that up for next to nothing, and brought it home and have used it ever since. But probably maybe about a year ago, maybe a couple of years or so, time time to me is a strange thing. Um, but yeah, a year or two ago, it started not being able to stay up at the right height. So it would zoom, 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 zoom. And over the course of a day, I would lose, 4 to 6 inches or so. And I I would I would continuously have to stand up, pull pull the lever to raise it up. As soon as I sat down, it would drop 2 or 3 inches or so. So I finally decided I've got another chair. It's about 1/10 as comfortable as that one is, but what it does is it gets me up to the right height, because yeah, angles are really, really important when you're working with um, computers, and especially as a programmer. um, having your hand at the right angle. I Knock on wood, I've been really, really lucky. I have i have been typing my entire adult life a lot. Okay. um, that's what a programmer does. It's types, right? And I have absolutely uh, no problems at all with my hands, wrists, fingers, arms, nothing at all. And I've thought about why, because people around me um, uh, who type not nearly as much as I have uh, would get all these problems. What's it called? Carpal tunnel, and aches and pains, and swelling, and even like tendonitis and all that. And you know, I would just I've just I've just sailed through all of that with literally no problems whatsoever. Um, uh, and so, I sort of wonder, it's like, well, why aren't I getting these kinds of problems? And the only thing I can think is, um, and this comes very, very naturally to me, and that is, um, after I've sat for mm, 20 minutes, half an hour or so, um, and done things, either just sat or sat and typed, whatever it is, I've had to stop, um, get up, move around, everything else, then come back after a couple of minutes. And it's something that I've always done, and that's my only excuse. That's the only reason why I can think that I haven't, developed tendonitis or anything else. Yeah, maybe it's posture. I don't think I have very good posture. I tend to slump and I mean, if I were to sit up straight, right, it would sort of be like this, right? But I'm usually, leaning back like this, trying not to slouch in front of the camera. But, in general, I don't think my posture is all that great either. Um, yeah, so anyway, I don't know how I got on that subject. I don't know. I don't know, because we're supposed to be talking about astronomy, right? But, a lot of what professional astronomers do is they are at the computer, right? They are analyzing their data, they are reducing their data, and they're either writing grant proposals, they're either writing proposals to make observations at telescopes, or they are writing papers. And if they're not doing that, they're um, grading papers, uh, you know, reading the latest journal articles, blah 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 blah. Yeah, I don't know if it's how I just sort of hold my arm and my wrist for a number of years, and I haven't done this in a while. Um, I had a little. I'm not exactly sure um, what it's called, but it's like a little foam pad that goes sort of in front of the keyboard, and that sort of, the keyboard is maybe an inch and a half or so off of the surface of the table, right? So when you type, you sort of have to hold your hand up in the air and type. And these little foam things, that went sort of all the way across the width of the keyboard were probably maybe 3/4 of an inch high or so, and you could rest your wrist on that. Maybe that's what it was called, a wrist rest, wrist rest, wrist rest, wrist rest, wrist rest, and that that allowed uh, me to, you know, not have to hold my hand up, because when you're holding your hand up in the air like that, your entire back, your shoulders, your neck, the whole thing is contributing to that force. But when you can rest most of the weight of your arm down on this wrist rest, I need to get one of those again. I'm sure they're available. Um, because, yeah, it looks like I'm going to be doing some more typing here. Um, but that really helped a lot. And I haven't had one of those in quite a number of years. What I use now is pretty much whatever I have on hand. I've got sort of some small flat items sitting around on my desk. Sometimes it's sometimes it's even this, right? That'll be laying on my desk, right in front of the keyboard, and I will actually, rest my wrist on that. Now that's only about maybe half an inch high, but it allows it's actually pretty useful for that. But yeah, I should get a wrist rest. Um, that was really nice. But yeah, that's what astronomers do. They spend a lot of time in front of the computer. Cheers. So, wanted to give an update to my telescope um, uh, um, parameterization project, seeing how well it can do um, photometry and um, um, astrometry, so measuring the brightnesses of targets and measuring their positions. The astrometry is really easy, and so I'm getting um, subarc seconds, um, um, accuracy, and precision with that. Really happy with that. My pixels are about 1 arc second in size. So anything less than that, anything less than about half of that, I'm like, that's awesome. Photometry, photometry is another thing, and I think, you know, last night I was talking about, the fact that um, you know I'm I'm making these measurements, and what I'm doing is I'm calculating the differences in magnitudes between one star and some other star, and so uh, I've just sort of um, arbitrarily chosen to say, okay, I will pick the brightest star in the field of view as sort of the reference, and then all the other stars I'm going to compare to that. So that's just a matter of measuring the flux from the reference star and the flux from, you know some other star or target in the field of view, calculating the ratio between those fluxes, taking the log base 10 and then multiplying by negative 2.5, and that gives me the difference in stellar magnitude between those two stars. Then what I can do is I can do exactly the same thing, but from a catalog of stars where uh, you know probably the measured magnitudes are correct. Um, and I can do exactly the same thing. I can look at the difference in magnitudes between those same two stars in the catalog, and then I can compare my measurement to the measurement in the trusted catalog. And what I was seeing was well, I mean, what I want is a perfect match, right? I mean, I want a perfect match, and I want repeatability. So every single measurement I make, um, I want it to be, very close to what the catalog says, and I want to be able to repeat that. So the accuracy and um, um, precision I want uh, very, very low, right? Very, very low, which means better. And what I was seeing um, was that, um, and you know, in hindsight, this sort of makes sense. And it was in the back of my mind, but you know how that kind of thing goes. Um, uh, I was seeing actually pretty good precision. I was seeing, you know, uh, better better than a tenth of a magnitude. I was seeing maybe zero point zero 0.05 magnitudes in terms of um, precision for some stars. Turns out to be for the brighter stars. Precision was very, very good, and accuracy was relatively okay as well. Um, but I was seeing a pretty big spread in terms of the accuracy, and so I've been scratching my head these past couple days, trying to understand, is there something that I'm doing in my process, in the code that I'm writing, that isn't right, and is causing this kind of weird thing. Um, and one thing I noticed last night, actually during this live stream, was that I've been looking at the absolute value of the differences between these two measurements, just because at the time I was just sort of, well, I wanted to get a measure of accuracy. I wasn't too interested if it was high or low, you know anything like that. Well, it turns out that when I'm seeing problems, I I want to know things like, well, you know are all my measurements being consistently lower than what the catalog says, or higher, or is it a mix? You know, don't know. So I just looked at the actual values as opposed to the absolute values, and it turns out this is still sort of a mystery to me, and it's definitely a red flag that I haven't been able to figure out yet. But all of my measurements are um, are very, very consistently uh, smaller than the catalog ones. Putting it another way, catalog measurements. So I can compute, the difference in magnitude between, star A and star B, and say it's, zero point 0.2 magnitudes. Okay. Well, pretty consistently, um, um, with my data, I can do exactly the same thing. I can do exactly the same calculation, and I'm getting, say, zero point 0.1 magnitudes or 0.15. It's always, it's almost, it's very, very consistently lower. So if the catalog says there's a difference between these two stars of 2.1 um, magnitudes, all measure 1.8. It always seems to be less. Now, not always, but uh, maybe out of 50 stars in a field of view, one or two is actually um, greater than the catalog one, but the rest of them all seem to be less. So that, to me, I would think that there would be an even spread, right? That about half of them would be, you know, a little bit um, greater, and half of them would be a little bit less. The fact that I'm seeing them all less than the catalog is still a red flag to me, but I can't figure that one out yet. So stay tuned with that. Um, what I've determined, however, and I'm going to talk about this as fast as I can because I don't want to bore you too much with these insane details. Cheers. But I do want to take you on this journey with me because I think it's interesting and gives me something to talk about anyway. So not as if I don't already have a lot of things to talk about. But what I've determined, um, you know, I looked at two more data sets today. I had another set of 20 images, 2-second exposures of Messier 41, and I had another set of 20 images, 2-second exposures of Messier 46, which is sort of right next door, a little bit east of M41. Um, and so I looked at both of those, and as I said, some of the stars uh, were were showing, pretty good accuracy and precision, and some of the stars weren't. And what I've determined, and again, it's sort of like hindsight is like, boing, right? But what I've sort of determined is that I just do not have adequate signal uh, in order to make either very, very accurate or precise measurements. The fact that in some cases my precision is very, very good, 50 millimagnitudes precision. So over 20 images, I'm consistent to um, 50 millimagnitudes in some cases. Now, in some cases, I'm consistent to 3 magnitudes. so, so it it uh, it's all um, it's just all over the place, and that is unacceptable for the kind of project that I want to do. So, pretty much what I have determined is that I just have a signal problem. I've got a low signal problem, and there's just uh, there's there is something that I can do about that, and this is going to be really, really interesting, but it's going to work. I've I've done I've done it before. I haven't done exactly what I'm thinking, but I've done all the pieces. So it's all I have to do is put some of the pieces, excuse me, some of the pieces together. So what it boils down to is that I have to stack images. I have to take 20 images and I have to add them up. Now, there are two problems that I have with doing that. The first problem is that this telescope does not track very well. It can do a 2-second exposure. It can do a 2-second exposure, maybe a 3-second exposure, and the tracking is quite acceptable. Anything more than 3 seconds, if I want to do 5 seconds or 10 seconds or a minute or an hour, forget it. Just forget it. Okay, no, not happening. Not happening at all. So, uh, so that's sort of the first problem with being able to just blindly stack. Just take a stack of 20, add them up. No, the stars are going to be all over the place, right? So that's one problem that has to be solved, and that's sort of the fundamental thing. Is that you know, I've got to be able to stack these things, and in order to properly stack them, I need to be able to uh, remove the tracking errors. Okay, so that's the first thing, and I'm going to try to go through this really, really fast. So I have to remove the tracking errors. The other thing that I have to do, because this is on an altitude azimuth mount, as the telescope moves through the sky, as it tracks through the sky, there is an apparent field rotation that happens. And so I have to figure out how to calculate what that rotation is over, if I've got 20 images that, um, you know, were taken over the course of, let's see, 20 images. It, if I do like a 1 second exposure each one, then that's 20 total seconds. My download time for this camera is like 15 seconds per image. So 15, say, grabbing the handy dandy calculator. Every good scientist will have a calculator on his or her desk at arm's reach. Now, an amazing scientist will have an HP. Okay, I do not have an HP. I am not that amazing. Okay, it's all I have is a Casio. It's a Casio FX 300 SA, but it is a scientific calculator that has served me well for, man, I think I've had this thing for 20 years now, at least, probably even a little bit more or so. It's solar powered, so it never dies. And yeah, whew, punched a lot of buttons on this thing. Anyway, how did I get off on that? Oh, yeah. So 15 seconds times 20 exposures is 300 seconds, plus the exposure times themselves, which is a total of 20 seconds. So I've got 320 seconds of time that, the telescope is tracking the sky, but because it's on this alt azimuth mount, it turns like this, and it just tilts up and down. The sky moves in a different way, so that causes an apparent field rotation. So over the course of 5 minutes and 20 seconds, there's a lot of um, 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 field rotation, several degrees. And so I have to, and this is the thing that I've never done. I've never had to calculate what the rotation is. Um, so I'm thinking about how to do that. Probably, yeah, I've got a couple ideas that I'm going to try. I'm going to try them tonight uh, after the live stream. The other thing that I have to do, which I haven't done yet, is I have to get into what's called subpixel shifting. So I cannot just move these things around pixel by pixel. I have to be able to move at least a hundredth of a pixel, if not more, and that's extremely easy to do. It's just a little extra code, and haven't done it in a while. So it's sort of like, you know, not riding a bike in 10 years or so. The first little bit, it's like whoa, whoa, and so that's sort of how I am at the moment. I also, I know what's involved in that code because I've written it several times, and it's just work. It's just painful, tedious work. So, which I always try to avoid if I can, but that rarely works out. So I'm going to have to stack these images. What that will do is that will increase my signal. So I'm right now, okay, I've got a dynamic range of from 0 to 65535. And with these 2-second exposures that I'm seeing like a maximum uh, value of like 600. Okay, so that's 1%. That's 1% of the dynamic range of this camera. Okay, it's I'm thinking about it now, and it blows my mind that I can do any kind of um, photometric analysis at all when I'm only able to grab onto the bottom 1% of the dynamic range of this camera. It's no wonder, no wonder the accuracy isn't all that great. The precision is pretty good, but as I said, one of the things that was sort of in the back of my head, but I didn't pay any attention until this morning, and that is which which ones are accurate and precise, and which ones aren't. And it turns out, mind blowing as it is, okay, that the bright stars I'm able to measure accurately and precisely, and the faint stars I'm not. Duh. So what I have to do is I have to be able to stack these images, and there's a couple of obstacles there in order um, to properly stack them, but I'm on it, and I should have hoping to have something in the next couple of days or so with that. I've got enough data that I don't need any new data at this point. Um, really, really, really quick and dirty stacking of 20 images got me up to a signal of about 7 or 8,000, almost 10,000, in fact. And 10,000, right, is what's 10,000 divided by 65.5, 65.535, 10,000 divided by 65535. That's 15% of the dynamic range. So that's a little better, and that can only get better as I stack more and more and more. So maybe I'll have to take 30 or 40 or 60 of um, these images and stack them up in order to get a good signal. But I am on it, and I'm hoping that once I'm able to properly stack, then I will run through photometric measurements again, and I will again look at the accuracy and precision of my measurements as they're compared to catalogs. Um, in this case, I'm comparing my stuff to the Gaia catalog, and yeah. So hopefully that'll go, and that'll be happening in the next few days. I'm going to have to give myself a few lessons on calculating field rotations, and I've got to go through a reminder course in subpixel shifting. But I've done all that stuff before, so it's just a matter of doing it. And the dread is that I know what's involved, and so it's like, tired. Cheers. All right, enough about that. So one of the other cool things that you can do without a telescope or binoculars or anything else, as long as you can see at night, you can watch meteors. And over the years, a number of meteor watching networks, automated networks, have come online. Um, this was an idea that I had quite a while ago. Never um, followed up on it too much, but I I am really pleased to see, all these things going on, because what they're doing, what they're fundamentally doing, is collecting data. Um, it's information about, the solar system, and sort of the stuff out there. And after you watch a while, this is the scientific process, right? You sit back and you watch. You watch nature do its thing. And after a while, it's like, well, all of these meteors seem to be coming some from the same place. What is that all about? And, you know, these meteors seem to be coming from over here. These meteors seem to be coming from over here. Um, these meteors I see in August. These meteors I see in July. Um, what's going on? You start seeing patterns, and the scientific process starts. And so, we've learned a lot about meteor showers, and why they occur, um, why they seem to um, be coming from um, one spot in the sky, all those kinds of things. So, what I'm going to show you here is just one of the networks um, that are watching for and characterizing um, meteors. Now, these guys are basically just looking for the brighter ones. So those are called fireballs. So they're not really sensitive um, to really faint meteors. These guys are just looking for the brighter ones. So in instead of a speck of dust, these are a speck of sand. Okay, um, sometimes bigger, but most of the bright ones that we see, uh, very bright ones, are specks of sand, maybe marble sized, maybe, right? Most of the meteors um, that we see are like little pieces of dust. They're tens of microns in size. They're just really small. So these guys are looking for some bright ones, and they have locations. In this case, just uh, in certain spots around the United States. You can see the Southwest is well represented here. The Ohio Valley, the I guess that would be like the Tennessee Valley, and then around Kennedy Space Center in Florida. This is a NASA sponsored project, as you can see up there. Um, and as I said, this is one of many in the world. I just uh, I know of this one, and their presentation is pretty cool. So I thought that we could just sort of run through these. So most meteors that we see uh, at night are, as I said, little grains of dust that are in orbit around the sun. and they cross that orbit crosses the the um, the path of the Earth as it's going around the sun. And so basically how you can look at it is that the Earth is running into this cloud of dust. And the theory is, and you know, pretty good evidence here. The theory is that these clouds of dust are more like a trail of dust that is left behind comets. So as a comet moves through, the inner solar system, it leaves behind itself this trail of dust. And if it just so happens that it crosses the orbit of the Earth, then there's a pretty good chance that uh, that the Earth at some point is going to um, 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 intersect that that path, and we're going to zoom through this uh, um, trail of dust, right? And so as we move through this trail of dust, um, of course, that dust hits the atmosphere of the Earth, and as the theory goes, it burns up, right? Because uh, they're moving very, very fast, and when they hit the atmosphere of the Earth, um, um, friction is created. They heat up, they vaporize, and that is basically the end of that. Now, larger pieces will um, not only look brighter, but some of them can actually make it to the ground, and that's what you would call a meteorite. When they're up in the sky, they're called meteors. When they're out in space, they're called meteoroids. So the same object, depending on its location, has three different names. English for you, huh? Yeah. Um, so uh, so as the Earth moves through this cloud of of dust, uh, all the meteors seem to be coming from the same place, and maybe that seems strange at first, but I'll bet that almost all of you have experienced a similar thing. If you've ever driven a car in a snowstorm and you look out your windshield, what you'll notice if you look, um, carefully, and it's actually much better if you're like the passenger doing this because, being a driver in a snowstorm, you don't want to be too distracted. Uh, but um, if you can take a look, you will notice that all the snowflakes seem to be coming from a point in space. And that point in space depends on a lot of things. It depends on how you're moving through the storm, what the wind is doing, all of this, right? Well, that point is called a radiant, and the exact same effect is going on as the Earth is passing through, this cloud of dust. Um, So anyway, what these guys do, they have these all sky cameras that are weatherproofed, but they're able to see the entire sky. They have um, um, a nice clear dome over them, to protect them from the weather. It looks like this one is inside of PVC, and then inside here you can barely see it is a camera lens, and that is like a fisheye lens, so it can see the entire sky, 180 plus degrees. of the entire sky. And then, of course, behind this lens is a camera. And behind the camera is some software that is looking for these events. And so, you know, they're watching this, um, these things every single night. Now, if it's cloudy, of course, you can't see anything. So you can go over here, and I know that the print is really, really small, but I'm going to click on a link called Live View, and this is a live view of the um, all the cameras in the network right now. And the ones in Arizona, I don't know which ones they are, but this one looks like, yeah, see, so here's a view of the sky. It says it's at 2:40 UTC, so that was like 10 minutes ago. Here's the moon. It looks like it's next to a bright star. Let's see. Constellation Orion down here. Here's Sirius. Uh, let's whoop. Let's see. Capella. Here's Capella. Um, Gemini. Where's Gemini? Gemini should be up here somewhere. I don't know. Kind of hard to see. They probably have an auto gain on this. So with the moon being out, things are sort of turned way down. So it's kind of hard to see any of the fainter stars, but you can see, the belt of Orion there. Um, Procyon is one of these stars. There is something else there too. Maybe it's a hot pixel. Who knows? But this is a relatively live view. Um, Again, I'm not quite sure where these are, but there are a number of these, as you could see in the map, spread out. So the idea is that if two or more of these all sky cameras see the same event, then they can sort of triangulate on that and um, figure out, how far away it is, how high up in the atmosphere it is, how fast it's moving. They can even, although this is a real stretch as far as I'm concerned, they can even calculate an orbit. So, as I said, that's a real stretch because, you know, these orbits, can be absolutely huge, right? On the orbit, on the order of, the orbit of the Earth, and we're looking at a section of it, maybe a few tens of kilometers long, where its orbit is, millions, hundreds of millions of kilometers. So, to be able to calculate an orbit, there's a lot of error in that, but it's still kind of fun. So these, of course, are the live views, right? So 2:39 UTC. How do you update this? I don't know. I guess this one here just shows a picture of the sky as it is right now from a particular location. It identifies a few of the stars, et cetera, et cetera. They use these stars as references in order to measure the brightnesses of these meteors. So what we can do is we can go and look at the actual detections. I'm going to take a swig of this hydrogen hydroxide here. Hold on one sec. Cheers. Awesome batch. So let's look at these guys. So what this is showing, as soon as I can scroll down, is so these are just detections. So these are all of the cameras, right? All of them. But in this case, only 3 of the cameras actually made some kind of detection. Now, what I'm going to do is I'm going to look for maybe sort of an interesting one. Oh, okay. Well, okay, here's one. So, um, so this camera witnessed this event. I hope you can see that on the screen okay. Little meteor event there. And at exactly the same time, this camera witnessed the same meteor. But as you can see, because the locations of these cameras are different, the where the a meteor seems to be in the sky has changed. So they can actually use this information to find out all kinds of things about it. Um, so what they do up here in the upper left is they give a date and a time. So this event happened on March 17th at 3:26:42 um, UTC. They calculated the velocity of this guy to be 23.3 kilometers per second. So that's pretty fast. They first saw it when it was 80.9 kilometers up, and it um, disappeared when it was 59.6 kilometers up. So apparently they have a resolution of like zero point 0.1 um, kilometers, like 100 meters or so. So that's not too bad. So there's a couple of links here. You can actually click on the image itself and you can download a short little movie. Let's see if this will actually work. You can download a short little movie. Let's see, let's do this a different way. Um, mm, okay, I was hoping, so I'm gonna have to save this. Okay, let me get myself set up first. Let me get myself set up first, and then we'll watch these short little movies. They're they're usually only a few seconds long. Um, but let me get in the right place here. Dun, 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 dun. Patience, patience. Okay, and I'm gonna do that. Okay, so now I'm gonna save this. Save this over here. Okay, it's saved. And I can go over here and come on. Oh, come on, you silly machine. I don't know why it thinks it has to index things right in the middle of my live stream. How rude. God. Dun, 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 dun. It's about time. Okay, so let's run this. I think, do I have this in loop mode? Probably not. I will get it into loop mode. Poor slow machine. It's trying. Be patient. I think it is in loop mode. There it goes. Did you see it? There it goes again. See, it actually marks where it is. So this is real time. This is a real time image. You can, I don't know if you can see the little clock down here. 41, 42, 43, 44, 41, 42, 43. So that's pretty real time, and just a nice little event there. It looks like they have it doesn't look very much in focus. It's really really noisy. It's really a dark 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 sky. I don't really see many other stars, in fact. So this was a pretty bright event over them. Allegheny. Allegheny. That's probably Allegheny, New York, right? So that guy, what did they say? He was moving about 20, 23 kilometers per second. And when you first saw it, so it's diving into the atmosphere. It's actually going down as well as moving across. Now we can only know that because the other camera, the other camera saw exactly the same event from a slightly different angle. To save it. That. Let's take a look at him. So this is the same event from a different location, slightly different location. There it is. From Hiram. I don't know where Hiram is, but there it is, exactly the same event. Now my understanding is that all of these cameras are um, uh, orientated the same way. So up is north, and I think they said counterclockwise is east. So this is east, this is south, this is west. That makes sense because we were looking at the moon earlier, and it's over in the west. So yeah, that makes sense. So, that other one saw the event towards its north. This system is seeing the event towards its east, and it's maybe a little fainter. The streak isn't as long. All this information they can use to triangulate. And as I said, I think they estimated that they first saw it when it was um, um, 80 kilometers up, and it disappeared when it was around 59, 57 or so. So again, this is real time. This is exactly what it would look like. Um, well, because it is. This is exactly what happens. Um, so they can take that information, and there are two links here. One is called summary, event summary, and this is an information packed graphic for sure. Okay, so what they're showing here, and I need to understand this a little bit more. Um, but this is just these are the two events. So we have sort of a peach colored one here and a green colored one here. And this is where they appeared in those two cameras, right? So this one was towards the north. This one was sort of towards the east. Okay. This this is a calculation of the height above um, the locations. Well, I guess the height above on the surface of the Earth, right? So this is going from over here. It's going from like 60 kilometers up to 81. Okay, and then this trail offset is also in um, 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 kilometers. I think this has something to do with of how its speed is changing over time. Don't quite understand that. But anyway, they're getting a velocity of 23.3 kilometers per second. Now these plots here are just profiles. So they've just measured the brightness along the path, right? Along the path as a function of time, right? So they start at 0, and these are in tenths of a second. So here's 1/10 of a second, half a second. So this event, at least here, lasted about 1.4 seconds or so. And what you're seeing is the brightness of the sky. So Don't know if this is real or not, but see, it brightens up and then it wiggles, 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 and it's getting fainter and fainter, but it's still wiggling. Don't quite. I mean, I don't know if that wiggle is real. If that's uh, don't know. So this is for one location. This is for location two, and yes, indeed, location two was fainter, but it's doing the same kind of wiggling. Uh, who knows? Who knows? Um, these are just error measurements. They do some kind of a fit um, and compute, the um, the errors in that fit, and so that's what that's showing. Here's their um, orbit determination, which I said is sort of, you can't get that good of an orbit from that small amount of information, but it's fun anyway. Here's the Earth, blue Earth. Of course, it intersected the Earth. Here's the Sun, Mercury, Venus, Mars, Jupiter. So, at least according to this little speck of, of dust, this speck of sand, had this kind of orbit. Now, the interesting thing, I guess, about that is that, maybe this follows the orbit of a comet, of a known comet. And so you can sort of make an inference if you believe this orbit, which, as I said, that's questionable. But if if you can believe this orbit, then you might be able to match it up, to the orbit of a known comet and say, oh, okay, that grain of dust came from this comet. And if you have like brightness measurements, um, even even better, would be some kind of spectral information, some color information, which I don't see here. But if you had color information, you could even determine or get a rough idea of maybe what it's even made of. And if you have a rough idea of what it's made of, and you also have sort of inferred that it's coming from a certain comet, then you can almost logically deduce that whatever this little piece of stuff is made of is probably what the comet is made of too. So, uh, lots of inferences, lots of sort of deductions, that kind of stuff. This is just a map. It's sort of hard to see, but it's showing longitude and latitude. And this little orange line with an arrow is where they say the actual path was. And um, camera number 14 that had the peach path was located there, and camera number 17 that has the green path is located over here. And so that's where they saw it. That's where they found it. And isn't that cool? Isn't that very, very cool? I think it is. So that's just one event, right? This event happened on the 17th of March at 3:26:42, and these go on every day in and day out. Uh, there's a real bright one there. Let's see if we can get three cameras. Here's four cameras going off at the same time. Here's two cameras going off at the same time. Two cameras, two. I want to get three. There's three. Okay, so this is exactly the same meteor. What it was detected by three of the cameras on March 19th at 2:53 UTC. So while this live stream was going on, um, 2 days ago, 2 days ago, we had a meteor event that was detected by this all sky system. Is that cool or what? I don't know why it scrolls around like that. It drives me insane. Let's take a look at a couple of these, and then I'll let you go because we're already past the hour. But I just think these are so cool. There it is. Has it finished? I don't know. Has it finished? Oh, I've got to do that. We finished? Let's watch it. I think we're finished. Yep. Oh, there it goes. Low on the horizon. I've got this on a loop, so it'll repeat a few times. You can see some of the buildings around it, some of the city lights on the horizon. There it goes. So that was one detection. Here's a detection of the same event, the same meteor from a different location. You done yet? I think so. There it is. Ooh, that's a slow moving one. So these movies are in real time. They don't last very long, just last a couple of seconds. But you know, putting it into loop mode sort of helps a little bit because you can thing happens, um, they're able to detect it. And then there was a third location on this one too. Okay, this is a nice long streak. Download that one and take a look at that one, and then look at the event summary, and then I'm going to let you go. These hours go by very fast, at least for me. Oh, nice. See how they brighten up really fast and then they fade out? It's pretty characteristic. So that's pretty cool. All right, let's look at a quick event summary here. So of course, 3 events, 3 locations, green, peach, and red. And you can see the same kind of information. Here's the green, here's the peach, and here's the red. Yeah, I'm not quite sure. I'm not quite understanding these plots yet. Here are the profiles again, just brightness versus time. And yeah, this was a long event. It's like 2.3 seconds long. So that's pretty bright. Here's the little arrow showing direction and how long it passed. Here are the 3 locations: the red one, the green one, and the peach one. And then again, here's a orbit determination, which yeah, there's not enough information there to actually do an orbital thing. But yeah, it's cute anyway. So I think that's very, very cool. I'm going to, let's see, how can I do that? I think I'm still screen sharing. Am I still screen sharing? I thought I was. I don't see my little thing anywhere. Oh, I see. I turned it off. Okay, we're going to do this again. I don't know why my little thingy went away. Okay, stop sharing. Stop sharing. Stop sharing. Hello? Hello? Am I here? I'm just seeing a black thing on my live stream. Share. Present to everyone. Okay. Come on. Technical difficulties right at the end. All right. Well, let me see if I can still be heard. Hold on one sec. Yeah, I can still be heard. So, look, I'm just going to get out of here for now. I hope everybody has a great evening. I don't sweat these technical things because this is a live stream and it's fun. And so, yeah, who cares? Whatever. You can still hear me. That's good enough. I'm going to get out of here for now. Thanks for coming in. Make sure to subscribe if you haven't yet. Share this around. Thumbs up, thumbs down. Bunch of links down in the description. Take a look at those. And yeah, I will see you again tomorrow evening. Astronomy Daily Live, 2 hours UTC. All right, y'all. I will talk to you in less than 23 hours. Bye bye.